Welcome to the Talking the Talk podcast, where we'll be exploring items of automotive technology and their journey into mass production. I'm Kevin Reid, the founder of Ireland Made, where we celebrate stories of Irish transport, past and present, and this is our podcast. I'm delighted to welcome my co-host, Automotive Engineering Consultant Mike Keane. Mike's consultancy delivers bespoke and sustainable transport solutions, and previously Mike has led vehicle development programs for Ford, Williams Formula One Advanced Engineering, Nissan, Jaguar, Land Rover, and Aston Martin. Mike has also worked on projects as diverse as hybrid supercars to off-road electric vehicles. But what is most impressive for me, Mike worked on the James Bond movie Spectre, and he worked on the baddies car, the Jaguar CX-75. In each episode, we're going to be examining vehicles that range from the 1921 German Rumpler right up to what Tesla and Lucid are doing today. In our last episode, episode 11, we spoke about the history of suspension systems. And in this episode, Mike and I are going to explore vehicle dynamics. Hi, Mike. What part of vehicle dynamics are you going to explore with us first?
I have suspension systems, vehicle dynamics, two hugely interlinked topics. Now, where the suspension system episode last time, we spoke about the tangible physical components, such as the difference between coil springs and leaf springs. Today, we're going to talk about the subjective attributes that describe how those components perform. So it's broadly divided into two terms, ride and handling. Ride is the ability for the suspension to isolate the occupants from the undulations and the impacts of the road. So, in simple terms, how comfortable are the occupants? And then handling, fundamentally, it's the ability of the suspension to keep the tires in contact with the road and pointing in the correct direction so that the car responds accurately to the requests of the driver.
All right, I'm looking forward to this because as a person who drives a 1965 Volvo Amazon with a lot of body roll and on skinny tires, this is going to be very interesting for me. Now, let's explore this. Dynamics and suspension design are not independent.
No, there's a mutual dependency between them, Kevin. So as suspension and vehicle dynamics became better understood in sort of the earlier days of development, it often became clear that the existing technologies at the time were just not capable of performing well enough to achieve the desired performance targets from a dynamic perspective. So as a result, that would encourage then the development of new components. However, the components were also subject to many other influences in the car design, such as the package space or the weight or the complexity even, and then obviously the cost. So a conversation about dynamics, it goes hand in hand with component development. Having said all of that, we're going to look at dynamics mainly from a chassis and from a suspension perspective and how the dynamic targets influence the design of those components. But it's actually a little reductive. Vehicle dynamics, it considers the inputs from many systems and attributes in the car, not just the suspension system. So, for instance, you have the activity of the powertrain, the aerodynamics, the braking and steering systems, even the mass distribution in the car. And then all of these would normally affect or do affect vehicle dynamics.
So that's a very, very wide remit. And we're not going to cover all the details of the actual engineering. Instead, today, what we're going to look at is the history of vehicle dynamics.
Right. Now, you and I, we often reference engineers and designers in our conversations, and we've often named specific engineers, sort of famous examples of them. In the Trendsetters episode, we talked about Alec Asiganis with the Mini. Giorgetto Giugiaro, was very prominent throughout the styling episode. And even in the last episode on suspension, we talked about Earl Macpherson, who developed the Macpherson strut. But actually rarely has one topic owed itself so significantly to one engineer as vehicle dynamics.
So that sounds like a genius. Does this genius have a name?
Absolutely. Maurice Olley, a man from Wales. So he was born in Wales in 1889. So we're going right back to the start of automotive development. He started an engineering course in the University of Manchester, but actually tuberculosis was rampant at the time and it cut his engineering short. So then sort of fast forward into 1912, then he joined Rolls-Royce in their aircraft division as a draftsman. And then subsequent to that, he became a tool and jig designer. And for a period, he was working directly with Henry Royce himself, actually, on a number of aircraft engine components. Then in 1917, Rolls-Royce sent Maurice Olley to America to study tooling design. and he worked with component suppliers for the Rolls-Royce aircraft engines. Now, a number of those suppliers were actually small car companies in their own right, and he did contract work with them. And that was sort of his introduction into car work. Then the following year, 1918, Rolls-Royce actually made a decision that they were going to build cars in Massachusetts in the US.
Really? So
Yeah,
I always had in my mind that they only build Rolls Royces in Britain.
no, absolutely. And it gives you an idea, like a real indication of the strength of their export market back at that stage. And of course, back then, as they are today, Rolls-Royce were sold to affluent buyers only. So they created a manufacturing arm in Massachusetts, and Ollie was given the position of chief engineer. And he was pivotal in expanding that arm of the company, and he worked there for the next 10 years. um, Rolls-Royce had a manufacturing division right up until 1929, and it was the Wall Street crash that killed off that division in the US. But at that stage, Ollie was settled in America. He was married. He had a family. He wanted to stay in America. So the following year, then Cadillac's chief engineer, a guy called Ernest Seaholm, he brought Ollie into Cadillac as a chassis engineer.
So now our story and our exploration, now we get into vehicle dynamics.
Absolutely. Yeah, absolutely. So in Rolls Royce, he gained a lot of experience dealing with sort of the inherent dynamic problems with the technology of the time. Now, bear in mind, Rolls Royce were state of the art, but still, state of the art at that stage was solid rear axles and solid front axles. And the solid axles, they gave particular ride and handling problems. And another thing is actually there was a lot of problems, vibrational problems, particularly on the front wheels due to unsprung mass.
Ah, so in the suspension episode, you had previously spoken about the solid axle translating on forces and movements basically from one side of the car to the other. In the context of this conversation, what do you then mean by unsprung mass?
Right. So unsprung mass is actually a very important concept in vehicle dynamics. So if we think of the four corners of the car in very simplistic terms, we have four wheels sitting on the ground, and they're then attached to the body of the car via the spring. So for you to think of this, right, so consider a very simple representation of wheels, springs, body, just sort of three elements, one above the other, very simplistically. The springs carry the mass of the body and actually everything that's attached to the body, right? So everything in the body includes interior, powertrain, electrics, glass, even the occupants. So the mass of all of those elements is in the body and that's carried by the springs. So they're suspended by the springs. So that mass then is acting on the springs simply through the force of gravity. And it's actually relatively easy for the springs to control that mass. On the other hand, if you go to the other end of the spring, you have the wheels. So the wheels are not suspended, they're not sprung, and the wheels are dealing with the various bumps and potholes and undulations, and all of those elements are putting these rapid forces through the wheel. So the mass of the wheels is pushing on the lower side of the springs with multiple, often high frequency forces. And the springs must also resist those forces coming through. Now, the wheels are on the lower side, they're not suspended. So we call that mass of the wheels the unsprung mass. The heavier the unsprung components, the more difficult it is for the springs to control them. Now, I'm talking about the wheels, but actually there are a number of components that are unsprung. So if you think about the brakes, the discs, the calipers, the tires themselves, the hubs, the uprights, even the air within the tires, that's all mass that's on the unsprung side. It's on the lower side of the spring. So the ability of the engineers and the vehicle dynamicists to limit that unsprung mass, that's key for suspension design. So, a good example of that, if you think of very high performance cars, think of something like Lamborghini Aventador. So that has carbon fiber disc brakes. So apart from the heat dissipation benefit of carbon fiber disc brakes, one of the big benefits is that they are much, much lighter. So they're helping to reduce that unsprung mass.
Right. Okay. Got you. Thank you. So take us back to Morris Ollie, his Rolls Royce experience. And at this stage, he'd been given, this stage in our story, the role of chassis engineer.
Yeah, right. So he came into Cadillac, he had a lot of experience from Rolls-Royce. And then at Cadillac, he was given a very important and very wide remit of just improving the ride abilities of Cadillac's product line. And Cadillac at that stage, they were, as they are today, they were a division of GM or General Motors, and GM, they were already leading the industry in terms of vehicle testing.
All right. Because in the safety episode, you'd mentioned GM, they started crash testing back in 34.
That's correct. So
Right.
they actually GM built the industry's first proving ground in 1924. So a proving ground, it's a purpose-built testing center. It includes test tracks and other testing centers or testing buildings within the proving ground facility. So the testing track part of that, then the tracks are purpose-built to allow engineers to carry out performance and durability testing. So the track might incorporate rough surfaces such as potholes or cobbles or gravel, or it may have low friction surfaces such as ice or wet roads, so that those real world conditions can be simulated.
Yeah, and the reason I'm smiling is it reminded me of Dave Allen, the comedian from the 1970s. Renault were advertising a car and they were showing their car going across the proving ground and all the things it was being subjected to. And he was looking at that going, if I wanted my car to do that, I'd borrow someone else's car. So
actually, it's a great example. The testing tracks, they're very aggressive, right?
yeah.
They will often mimic very specific pieces of real world testing. So real world roads outside. So they find a very bad condition road and they will replicate that exact bad condition road. I hate to say it, there was a period of time in the UK where the JLR had the Irish road test.
I know that. I do know that, yes.
But so that's all sort of the robustness and the durability testing. But they also can do the performance testing. So the proving grounds, they often have long, fast sections, often with high-speed banking, and that allows continuous high-speed driving or emergency maneuvers or braking tests. And then as well as that, as I said, the proving ground, as well as the test tracks, they have a number of indoor tests where they have sort of wind tunnels or climatic chambers or shaker rig testing. And then car companies then put their prototype vehicles through a sort of a predetermined test plan that will work its way around those various tests.
So Ollie, what he had then, he had access to the proving ground, all of the variable surfaces. He could take the car through the full remit of testing.
That's right. Yeah. So he had this wide remit and he had this fantastic state-of-the-art industry-first facility available to him as well. Now, he brought some testing ideas over to GM from Rolls-Royce. So in particular, a bump test that Rolls-Royce were doing that allowed them to test how a pair of wheels would interact on a single axle. But really from there, he introduced a whole series of test plans, developed test equipment and techniques that allowed him to observe and to investigate really in detail how the tires and the suspension and chassis interacted with each other. The real strength of Ollie was that he was very analytical, right? So he was very good on theoretical, mathematical first principles, but yet he simultaneously understood that ride performance, it's subjective, and indeed handling performance, they're subjective. And then he took that subjective understanding and then translated that back into suspension component design, so that those components could deliver the required field. So it was a very full understanding of all of the elements.
Right, that was a full understanding, but I don't have a full understanding because I've got an engineer talking to me about something that's subjective.
Yeah,
You're going to have to explain yourself here, Mr. Keane.
Yeah, right. So, okay. So engineers, we talk in terms generally of objective, measurable data, measurable targets. And that's how components are designed. That's how systems are designed. But when it comes to something like ride and handling, ultimately it's a subjective attribute. It's how the occupant or how the driver is feeling and how that feedback is coming back into the driver. And really it's only when you put all of those parts together into a car and test them on a proving ground that will come, that you can really get a true understanding of what that is. Now, long before the days of computer simulation, we have very powerful computer simulation today, but long before those days, Ollie was in a territory where, any calculations were done by hand, really. Now, he understood, and he studied and he understood the theoretical principles about vibration and oscillation frequencies. And he understood that ride performance centered around two primary frequencies. There's a pitching moment or pitching motion. So what that means is if you look at the side of the car, as the front of the car goes up, the back goes down, sort of like a seesaw sort of movement. And then the second primary frequency is a bouncing motion. And that's where basically the whole car rises and falls as one. So the theoretical modeling, so the paper mathematical analysis could predict what should happen. But really understanding how those two motions interacted with each other in sort of a complex real world environment, that could only be understood through physical testing.
And even today, with the power of modern computer simulations, proving grounds that are still used by the manufacturers?
Oh, absolutely. Yeah, absolutely. So, as I said, we have very powerful, accurate, detailed computer simulations, but really it's only when you put all of the elements together in the car and you have sort of the nuances of the materials, the nuances of the assembly tolerances, the nuances of even how those things perform in sort of, let's say, in climatic conditions or in maneuver and dynamic conditions. Um, if bearing in mind it's a subjective understanding we want to get, we can only really get that, our engineers can only really get that ultimately from proving ground testing.
Hmm.
So Ollie, he was the start of a generation of engineers who understood that. And what he did is he modified a Cadillac sedan with two large frames, one at the front, one at the rear. And he had these removable weights on the frames. So he could add or he could remove weights from it. And when he did that, he could change how the car performed in relation to those two motions, that pitching motion and that bouncing motion. And then from this, then he understood, like, learned lots of things. But like one specific thing that he understood that we still, that engineers still recognize today, is that a stiff front suspension has a much more significantly negative effect on the comfort in the car than a stiff rear suspension. And again, as we said earlier, bearing in mind cars at the time were all solid axles, including at the front axle. So that understanding then from Ollie and from his team, it led to the development of firstly independent front suspension, and also even further than that, it led to the development of the short, long arm suspension arrangement that we spoke about in the last episode.
Right, because we spoke about both of these in the suspension episode, and as I understand, yes, GM were the first to introduce both in the 1930s, and then how a variation of both of these are still used in nearly all cars today.
Yeah, absolutely. So, we're going back, like this is still the 1920s, 1930s. It really set a standard for how the industry thought about vehicle dynamics, performance, how the industry carries out testing and develops the cars. And as you rightly say, Kevin, even how those components and features were developed that we still see today.
Wow. So, I mean, this was groundbreaking work, but I say the story doesn't stop there. What else did he do?
Yeah, no. So he retired in '57, and he was prolific right through his retirement, developing tests and developing products. In 1952, he was made head of R&D, head of research and development at General Motors. And in that role, then, one of his very first programs was that he was responsible for developing the chassis for the new first generation Corvette.
Wow.
And even going back to the dynamic conceptual work, as is often the case in any kind of development work, when you solve one problem, you introduce another problem, sort of the law of unintended consequence. So the development of independent front suspension really introduced a new vehicle dynamic characteristic, and Ollie himself called that understeer.
Hmm.
So Ollie then, to look at understeer, he then spoke to the Goodyear tire company, and he asked them to give him data on the forces that were acting on the tires. And in fact, in order for Goodyear to provide that data, they themselves had to develop new testing techniques. So, his influence is migrating throughout the industry. So he looked at the tire data, and that really became key to understanding and solving understeer, and as well as multiple other characteristics. And then understanding the tire, that the tire is a key component in the chassis and suspension design. That's critical even today. And that relationship between tire companies and car companies, it's still a critical partnership even today.
Wow. So, like Ollie, he played a pivotal and critical role for decades.
He did. He did really. Kevin, it's really difficult to quantify the effect he had on how cars were designed and developed. One way we can look at it, right? If you think about how often you and I have spoken about him in across this podcast series, but without actually mentioning him, right? So if I give you a few examples, right? So he developed the concept of roll center and roll axis. Now we spoke about that in a good bit of detail on when we talked about the Chevrolet Corvair in the safety system episode. Ollie developed the analysis of lateral weight transfer. We talked about that in fuel tank design on the fuel system episode. He did analysis on drum brakes, which we looked at in braking. He did an analysis on the swing axle, which we looked at actually again with the Chevrolet Corvair. And then if you just more generally think between the steering and the suspension episodes, we've talked about camber, caster, Ackerman steering, bump steer, anti-roll bars, understeer, and oversteer. And they are all characteristics that he analyzed and developed. It's funny, I've picked up on the Corvair twice there, right? You remember we talked about it in the safety episode quite a bit, Kevin, and there were some questionable design decisions made, particularly around chassis and dynamics, and it led to those safety concerns that were held at the time. It is somewhat ironic that the Chevrolet Corvair, was a General Motors product, considering that Ollie was head of R&D at GM. But to be fair, he had retired by the time the Corvair was launched, so he can't take the blame for that one.
He was well gone at that stage. Okay,
Right.
so let's take our conversation back to vehicle dynamic characteristics. Let's say two easy ones. We've got understeer and oversteer. What do they feel like for the driver, and how does the driver deal with them?
Yeah. Okay. So two pretty common terms. So understeer is where the car is cornering on a radius that is larger than the one that the driver has requested. So, or in more simple terms, the front tires are starting to slide out towards the outside of the corner instead of tracking around with it. And oversteer is the opposite effect, where the rear of the car starts to slide out in a corner, or in sort of dynamic terminology, the car is taking a smaller radius than that the driver has requested. Now, any car can experience both of these due to a combination of design intent, so let's say suspension design, and driver input, so weight transfer and tire grip levels. So the driver has a lot to do with those things. Now, broadly, most road cars today are designed towards understeer, and it sometimes it's due to just simply package layout, so there might be front wheel drive, but there is also a deliberate intent by the car manufacturers to promote understeer from a safety perspective. If we look at the total grip within a car, it must be balanced between the power and braking and cornering, and often that's done simultaneously, actually.
All right, because on this conversation is reminding my friend Shane McGann from Longford. He's a rally driver, and his skill allowed weight transfer in the car. He intentionally transferred the weight in the car by either utilizing understeer or oversteer in a completely controlled manner, which always increased the forward speed. And I remember him describing it to me as weight transfer. He was doing it on purpose. So the two things that were happening in the car, we were going faster and I was screaming a lot. Very, very good at it. So back to this circle of adhesion. We spoke about that in the braking episode.
Yeah, we did. That's right. So the circle of adhesion, it's an imaginary concept that allows you to visualize that total grip that's available. Now, when we spoke about it, we looked at it from the perspective of the whole car, but it can also be applied as a concept to a single tire or to a set of tires. So if we consider the driven wheels in a front wheel drive car, if a car is cornering at maximum lateral grip, it's going through a corner, there's no more grip available, it's all been given over to cornering grip, and either a braking or an accelerative input is applied to the front tires by the driver, then the tires just become overloaded. There's too much grip, too much is being asked of them, and they lose adhesion. So from the driver's perspective, the steering wheel will be turned, but the tire loses grip and the car slides towards the outside of the corner. Now, the remedy for that is to reduce at least one of those inputs. So reduce the cornering input, reduce the braking input, or reduce the acceleration input. And you do that until the grip is recovered.
Right. So reducing cornering input would mean straightening the steering wheel.
Yeah, it would. Right now, so that's quite counterintuitive. So for a lot of people, if they're experiencing understeer, they'll actually increase the steering angle and they'll turn more into the corner. So it's sort of an attempt to somehow force the car more around the corner. But, in very simple terms, if the tire has lost grip at a given steering angle, if you increase that steering angle, you're not going to find the grip, right? You're just going to make the situation worse.
Yeah, so that as you say, it's counterintuitive. But you did say that understeer is designed for safety. How's that safe?
Right. So because if the car is sliding straight out of the corner and the driver doesn't apply sort of an appropriate remedy, so in that case, they add more steering. And actually all that's going to happen is that the car will simply continue on that same trajectory. So it'll keep sliding, relatively forward motion until it slows down to a stop or until it gains grip. But on the other hand, if a car is in an extreme example of oversteer, so the back is starting to slide around, starting to come around, and the driver loses control of it, it will start to spin down the road. And the trajectory of that spin, it can change trajectory very easily, and it's actually uncontrolled. So for that reason, understeer as a natural tendency in a car is safer if you consider the sort of vast majority of the populace are not highly trained drivers like you're a rally driver.
Yeah, fair enough. Like Shane McGann. So to summarize, then, the front wheel drive cars experience understeer, and a rear wheel drive car experience oversteer.
That'll be sort of a natural tendency, right? That's definitely a natural tendency, but actually any configuration can experience understeer or oversteer because of the influence of weight transfer. And again, this is about driver input. So I'll give you, a classic example of that was the Peugeot 205 GTI. Brilliant little car from the early 80s.
Great car.
Yeah. Light, fast, nimble, lots of fun to drive. The 205 had a fairly common suspension arrangement of independent McPherson front and trailing arm torsion beam at the rear. And we spoke about all of those actually in the suspension episode. And that combination, it was cheap to make, it's easy to package, and it could be set up to give not very nice handling. But some of the negatives with that is that the torsion beam is quite stiff, and the trailing arm doesn't allow any camber gain when you're cornering. So under heavy braking, weight is transferred to the front tires, and it reduces the grip on the rear tires. If the car is then cornered, the rear tires would lose adhesion entirely, and the car would oversteer. So if you turn this, if you order that the other way around, and you say in a corner someone is cornering and then they brake, we call that lift off oversteer. And many a 205 GTI, Kevin, was it was reversed through a hedge as a result of that characteristic.
Yeah, but reversed through a hedge with style.
Yeah, right, French style, right?
That's fine. Thank you, Mike. So join us for episode 13 when Mike and I will be exploring the history of motorcycle suspension. See you then.
Thank you for joining us today on the Talking the Talk podcast. My thanks to Mike Keane, and you can check out his consultancy on mikekeane.ie. Then check out irelandmade.ie to view our back catalogue of videos celebrating stories of Irish transport, past and present. We look forward to welcoming you onto our next episode where we further explore the origins of automotive technology. You can find us on YouTube or Spotify or wherever you get your podcasts. Please subscribe and tell your friends. Bye for now.